I'm going to be talking about decarbonizing the built environment. Can you hear me okay? Is the mic good? Yeah, thumbs up. So at the same time, I don't want to turn this into a train sales pitch. I'm an ops role at Train, not a sales role. So I'll try to keep this as industry specific and really talk about where the industry as a whole is going. I was going to start off with a little bit about me, but I was introduced with this long list of accomplishments, so I appreciate that. Yeah, I'm really pleased to be here. I'll just say a little bit about my team. I really want to acknowledge my team, my coworkers. I have a team of dedicated energy engineers, project developers, project managers, monitoring and verification people that really get the work done, and they really solve our customers' building-related problems. That's mainly mechanical and electrical infrastructure rehabilitation projects. Oh yeah, I gotta change slides. So if you're here today, I assume you know what decarbonization is. The intent is to look at decarbonization through the lens of HVAC, why it matters so much to a company like Train. I'm going to talk about the why, the what, and the how of decarb in the HVAC space. People think of Train as an equipment manufacturer, but we like to think of ourselves as a building and energy solutions provider. By the way, Train's purpose is to boldly challenge what is possible for a sustainable world. So now let me kick it off with the why. The built environment contributes roughly 40% of the CO2 emissions, global CO2 emissions. That's a huge number. Roughly 27% of that is related to building operations. So if you think of, oh, I can see the screen down there. If you think of HVAC, if you think of HVAC being half of a building's energy spend, that's a good rule of thumb. It's probably on the low side. That's 13 or 14% of the world's CO2 emissions is affected by HVAC. So for an HVAC manufacturer, we could take a glass half empty or a glass half full approach, and I'm here to say we're all in glass half full. But first, I want to give you a little bit of Decarb 101. So we have our scopes of emissions along the top. We have on-site emissions, mainly natural gas consumption. It could be any fuel burnt on site, oil, gas, propane. It could be fuel use, diesel, gasoline used by a fleet on site. And then we have refrigerants or refrigerant leaks. Scope 2 is most of that's going to be electricity generated off-site. It could be steam, chilled water, heating water, compressed air. Majority of that is going to be electricity. And then Scope 3 is anything related to the value chain of the organization. Really, in the commercial building space, buildings, it's carbon that's tied up in the construction and the renovation and demolition of the building. So that material extraction, raw material processing, construction, fabricating, that kind of thing. So that's our scopes. So along the bottom we have mitigating measures, solutions. So scope 1 would be energy efficiency, natural gas energy efficiency, refrigerant management, and electrification of heating. When I started my career, we used to call electrification fuel switching. I think back then we were switching from electricity to gas, and now we're switching back. How times have changed. Scope 2, we've got electrical energy efficiency and renewable energy. And then Scope 3, we have embedded carbon. So you add all that up, and that's decarbonization of the HVAC space. These are all articles. They're all articles you can Google right now. Please Google them on the break. The point of these articles are that The decarb space, it's polarizing, it's confusing, it's crowded. There's advocates that are arguing that we should be doing more. There's protesters that are saying we're doing too much. My gas went up on April 1st. I'm complaining. The point is that it's a confusing space. It's become political, unfortunately. So I just wanted to share you some real business drivers for decarbonization. The first is we've got BlackRock. So BlackRock, everybody's probably heard of BlackRock. It's the largest investment firm in the world. They state on their company's website that when they invest in a business, they look at their ESG goals, they look at their decarbonization plans, they interview their executive team, and they really vet whether ESG is important to the organization or whether it's just greenwashing before they invest in a business. Second to that is we talk to our customers all the time. Our manufacturer customers are telling us that their customers, so the likes of Walmart, Costco, they're coming to them, our customers, and saying you gotta do something about decarb. You gotta reduce your emissions. You gotta show us your ESG goals. Our commercial customers here in Ottawa, it's particularly an issue. They're telling us that they cannot rent, when their tenants' leases come up, they cannot rent their space unless they have a fully vetted plan to get to net zero. That's a real problem here for the commercial landlords in Ottawa, where the federal government rents a lot of space. In addition to that, we have our higher ed customers. They're telling us that students look at a university's ESG goals before they embark on their post-secondary education. U of T is a big leader here, as are some of the other larger universities in the U.S. So students are picking universities that have well-developed ESG goals around carbon reduction. So next you have the Carbon Disclosure Project. How many people have heard of the CDP? Anybody? Yeah, you. Andrew has. Somebody there. So the CDP is a not-for-profit third-party organization that vets organizations' ESG goals, their GHW plans. There was 23,000 organizations registered in 2023 with the CDP, sorry. So now you have this, you have investors, you have B2B customers, you have tenants, and you have students, university students, all have a place to go and fact check whether the organizations they're interested in are how they score on their ESG goals and their decarbonization plans. That's a powerful message for decarb and around HVAC, around buildings. So Train has developed a four-pillar strategy around decarbonization. The upper left-hand corner is electrical energy efficiency. We have in the upper right, we have natural gas energy efficiency and decarbonization. In the lower corner, we have renewable energy. And then we have refrigerant choices down in the bottom right-hand corner. If you split that down in two, you've got scope 2 over there, scope 1 over here. And that kind of ties back to the Decarb 101 slide. This is just, I'm not getting the build. My slides have the build feature, and unfortunately I'm not getting that. That's why they're throwing me off a little bit. Anyways, this is just a kind of a recap of the last slide. Solutions, how to get to carbon neutral. Energy efficiency, you've got that on electricity, you've got it on natural gas or fuels. Renewables, both cases, electrically and thermal. Electrification of heating. And then you've got lower GWP refrigerant. And then really important with refrigerants is when they leave your site, when they leave a building, they have to be disposed properly. So the first thing I'm going to talk about is energy efficiency. This is, after all, the Association of Energy Engineers, so I got to start with energy efficiency. It doesn't sound that fresh or new. This organization's been around since '77. People have been trying to save energy in buildings as long as energy has been consumed. Really, for cost reasons, the industry's shifted. The real driver now is doing the right thing and trying to get GHG's emissions down. So the first thing we want to start with is you take Canada's emission landscape. You've got your GHG emissions on the left-hand side. They're broken out by per person, per capita on the top, and by GDP on the bottom. And here we have emissions broken out by sector, and buildings are 13%. Big chunk is oil and gas, transportation. I don't know how, if gas consumed by buildings is included in blue or included in green, but let's just stick with 13%. That's a pretty big number. All we want to do is start with getting that 13% down to 12, 11, 10%, just really reducing the energy usage in the building. So some strategies. We've got building envelope. We want to reduce the heat loss, reduce the heat gain in the summertime. We've got, use newer equipment. You want to make sure you're using the most up-to-date stuff. You're taking advantage of all those incentives that are out there that we heard about. Your equipment complies with code changes. We've got lighting, LED lights. Big fan of lights, LED lights. When I was at Sick Kids, I retrofitted 39,000 light fixtures. I used to have 2 FTEs. All they did was change light bulbs. I think they changed light bulbs and hid in the hospital, but that's beside the point. But after the LED lighting retrofit, we were able to free those resources up and got them doing more productive value-added stuff. The next thing is controls, BAS controls. BAS systems have been around for 40 years. Trane's been in the business almost that long, BAS controls. And when we talk about decarbonization projects, one of the things I get excited about is demand-based ventilation. So really, tracking the building's ventilation load to occupancy. That'll have a big impact on greenhouse gas. If you think of a building's, sort of fuel usage, kind of that energy pie, you've got heat loss to the perimeter of the building, you've got ventilation, and then you've got your potable water. And then if it's a process or industry, you've got your process usage. So really getting the ventilation loads down. One of the things I'm really excited about in controls is analytics and using AI. So a couple things have happened. The cost of cloud storage has come down in the last 10 years. It's dropped considerably. And then kind of the rise of AI being, more commonplace. So where, in the old days, if you wanted to trend something, can you trend that supplier temperature? And, it would trend for a couple days and then erase over itself. Nowadays, data gets pushed up to the cloud, and we use AI to analyze that data. We use it to optimize the building use, reduce energy, and we also use it for predictive maintenance and preventative maintenance. So, really optimizing when we do maintenance, when we clean tubes, that kind of things, rather than just doing it once a year, and then also if things are potentially going to fail prematurely. The last thing is water. Canada, we're blessed here with a lot of water. I'll say that in my career, 30 years, water's gone up by 5 times. It's probably double of what electricity and gas has. So from a financial point of view, it makes sense to save water in a building, and it's just the right ethical thing to do as well. So the first big part of decarb that I'm going to spend some time on is electrification of heating. After you've done your energy efficiency projects, here in Canada, we've got a clean grid. We burn a lot of natural gas. we're a cold climate. That really leaves electrification of heating as a big rock as it relates to decarbonization. So much so that I think people interchangeably mix decarb and electrification of heating. They're not the same thing, but I like to think of electrification of heating as a subset of decarb. So when we're embarking on an electrification project, first thing we want to think about is the grid. Fortunately, here in Canada, the grid's quite clean. On average, we burn less than 20% of our electrical generation comes from burning fossil fuels. Coal, natural gas are big ones. We're blessed with a lot of hydroelectricity. Ontario and New Brunswick had made investments into their nuclear fleet. So first thing we want to think about is the grid. Our grid is 400 pounds per megawatt hour. That's about 180 grams per kilowatt hour. I apologize that it's up there in pounds, but roughly 180 kilograms per megawatt hour or 180 grams per kilowatt hour. That's pretty clean. Here in Ontario, it's about 40 grams per kilowatt hour, and I think in Quebec, it's about 1/10 of that. So you want to consider, next thing you want to consider is if you're thinking about developing a project in a grid that's not as clean as Quebec's or Ontario's, maybe Nova Scotia, you want to think about what the grid is going to look like over the life of the project. Places like Nova Scotia, they're cleaning up their grid, they're putting in renewables, big wind generation. So you really want to take a look as you life cycle out the project. You want to look at the grid, the impact of the grid, 5, 10, 15, 20 years out. So when you think of electrification, I'm not going to stand up here and talk about electric baseboard heaters or electric duct heaters or electric boilers. The hair on the back of my neck goes up. I think when I started my career, we were ripping those things out and putting gas heat in. So that really leaves heat recovery and heat pumps. You think of either of those, the first place you got to start with is, well, where's the heat going to come from? You've got all kinds of options. You've got ambient air, so air source heat pumps, geothermal. We've seen a big uptake and interest in both technologies. You've got sewer and storm water. I was fortunate to be involved in Noventa's project at Toronto Western Hospital. It's the largest of its kind. They're literally using special heat exchangers to extract heat from the city's sewer line that runs underneath Bathurst Street. That raw effluent, I'll call it, is roughly about 17 C year-round. It doesn't change that much. It's maybe a degree colder in the winter and a degree warmer in the summer, but they're using that as the heat source for large heat pump chillers, heat reclaim chillers that we were fortunate enough to supply. So I'm grateful to be part of that project. It was a pretty cool learning experience. Next, we've got lakes, rivers, and ponds, sometimes referred to as open loop geo. These are a real good source of heat. Obviously, you need a lake, river, or pond on your property, so it's kind of location here. Next thing, we have our ice storage tanks. I've got a slide dedicated to ice storage tanks. And then last but not least is exhaust heat recovery. I really think this one should be first. This is going to give you the warmest stream of air of any of those 6 to recover heat from in the wintertime. And it really should be probably the first place you look at is, what are you doing to extract heat out of the exhaust airflow. As mentioned, my previous job was with sick kids. We had Kashim, I think I pronounced his name right, talking about labs. So I had a 750,000 square foot lab building. It was a $400 million investment. They had 700,000 CFM of outside air running through the place. Let that number sink in.
So we had, and he kind of talked about general exhaust and fume hood exhaust, but we, roughly 70% of that air was what I'd call general exhaust. It was relatively clean. We captured that and used that in heat wheels in the air handling units. And then the 30% remaining, I'll call that the dirty exhaust. So that was fume hoods, specialty lab exhaust, toilet exhausts. That was all captured, and we ran that through coils, basically coils that had chilled water in them, and that chilled water was an artificial load for the two heat reclaim chillers. We had a heat reclaim chiller that would produce 140-degree water, F, and 170-degree water. So they provided heat to the various heating loads. And that dirty exhaust, that was a variable exhaust. It changed depending on the most of that exhaust was the fume hood. So people leave the sashes open, then that exhaust went up and the general exhaust went down. So there's a question asked about can that airflow be variable, and that's how that operated. Moving on. This slide here, there's a lot here. Let's check myself for time. There's a lot on this slide. Basically, we've got our electrified heating and cooling products up here. This could be anybody's equipment. It just happens to be Trane's equipment. On the top, we have unitary products. So those are anything from single-digit tons up to 75, 80, into the low hundreds of tons. We've got our applied hydronic, starting with air source, heat pumps and chillers. Has this thing got a laser on it? I guess not. Starting with our air source heat pumps and chillers, then our water-cooled product. So anywhere from hundreds of tons into the thousands of tons. And then we have our airside products along the bottom. Just a few highlights here. Big fan of VRFs. They're really, really flexible. You can mix and match with the different components. I was involved in a project. My team developed and implemented a project in a 100-year-old historical resort in Nova Scotia. This was a facility that was only used, it was owned by the province. It was only used in the summertime. Some new owners bought it. They were a little bit more business oriented. They came to us and said, hey, we'd like to occupy this building all year round. Do you have an HVAC solution for us? And my team went to work and we came up with a VRF solution. And now that facility is able to be occupied all year round. We ended up going with, I think there were 20-ton condensing units kind of selectively located around the property, and we were able to hide the refrigerant lines and still keep the historical look of the facility. Packaged heat pump, dual fuel heat pumps, available with electric heat or gas backup. Big fan of these, really great for the retrofit market. If you've got a shopping plaza, a school, something with rooftop equipment that's gas heat, electric cool, you can take these out, put heat pumps in, use the existing electrical infrastructure. This will get you, 70% GHG reduction, 75%. Basically, cut the lion's share of the gas load away. But you've got gas backup there for the really cold days, and you can do all that with the electrical infrastructure that's already in the building. What else do we got here? We got our water source heat pump product line. They would be used with geosource heat pumps. In terms of air source, we got air source heat pumps. They can be heating or cooling at different times. Then if you move along, we have air source heat pumps that can provide simultaneous chilled water, heating water at the same time. Lower down, we have our centrifugal chiller product line, so a conventional cooling only chiller there first. Our chillers can be ordered with a double bundle condenser barrel. So It's, essentially you have two sets of condenser connections. You have a set that would go to the cooling tower and a set that would go to a building's low-grade heating loop. These are a real good solution if you need a lot of low-grade heat, so anything, 115F and less, and you have a decent chilled water load all year round. I had two at the hospital, two at 550 tons. Next, we've got our agility chiller. So this is a mag-bearing heat recovery chiller. I think it caps out at about 440 tons nominal capacity. It'll produce more than 130-degree heating water with standard chilled water conditions. So it's a good heat reclaim chiller. Then we've got some packaged heat pumps, 4-pipe and 6-pipe. Again, the more the pipes, the more the flexibility, heating, cooling, heat rejection, all at the same time. I guess I'll make a comment in general about the industry. The industry is being challenged to create heat pumps that will produce higher temperature heating, so higher temperature hot water at lower ambient temperatures. So hotter hots from colder colds. So that's we've got solutions. Old heating standard used to be 180 degrees, 180 out, 160 back. We have retrofit solutions that can replace boilers with heat pumps. We got our airside product along the bottom. We've got catalog air handlers, semi-custom and custom air handlers, our terminal products, and then our VAV products. I'll make a comment that contradicts my last comment. Is when you select the airside products, when you select heating coils, even though I just said we have solutions that will go to 180 degrees, I really encourage you to go, kind of medium temperature, 140, 130 degrees. Notwithstanding the fact that we have solutions for higher temperature hot water, efficiencies, COPs, they're always going to be better at that lower temperatures. It's physics. It's just less lift. We have our next we have our storage heat pump system. So this is a pretty neat, innovative solution. It makes use of a lot of different equipment on the roof. We have a air source heat pump. In the basement, we have 2 screw water-cooled chillers. So those are our RTWD product line. They're a real workhorse for heat recovery. Over on the right-hand side, we have our beautiful thermal energy storage tanks. So those are tanks roughly 8 feet diameter, maybe 9 feet high. They hold roughly 12,000 gallons of water. There's a serpentine heat exchanger inside. And what we do is we cool those tanks down and freeze them into ice. So we're basically heating the building using ice. A little bit of a mind shift. You got to think about this system as it's not creating heat, it's just moving heat around in the building. So we're taking heat from areas of high heat gain, so maybe data rooms, areas that require cooling all the time. We're using that as a load on our heat reclaim chillers. We can be extracting, we'll be extracting heat from our exhaust air. We'll be extracting heat from heat that would normally be rejected to the cooling tower. And we can extract heat from outside using the air source heat pump. The nice thing about the thermal ice storage tanks is it decouples the time factor. So if you think of a building, heating load is highest in the morning, the cooling load is highest in the afternoon. 9 times out of 10. I mean, there's exceptions. Think of this room. It was 4C outside. They probably brought the air handlers on, maybe 6 a.m. They started running them, bringing some fresh air in, flushed the room out. It would have been a heating load. Now we've got all these people in the afternoon. It's 2 o'clock. The sun's up. It's 15, 16 C outside. We're in kind of a cooling load now. So we would freeze those tanks in the morning using heat reclaim chillers. take that hot condenser water, use that to heat the building, and then in the afternoon, we thaw those tanks out and use them to supplement the chilled water requirements. The other interesting thing about those tanks, I know this is a decarb presentation. We're talking mostly about heating. Those tanks can be used for global adjustment curtailment in here in Ontario. GA busting. I think most of everybody knows what GA is. I don't have to. Anybody not know what global adjustment is? Everybody. So they could be used for as a to reduce for GA curtailment to cut your peak demand in the summer months in order to bring the overall cost per kilowatt hour down in the building. So that's a nice option when you think of a decarb project that's going to cause electricity to go up, and then you do GA curtailment that will cause your average rate to go down for electricity. Next thing we kind of on pillar that sometimes goes unnoticed is refrigerants. My friend Sean talked about refrigerants a lot, so the entire industry is being there's regulations or there's in order to limit GWP of refrigerants, there's a compliance in place that we've got to get to certain goals to minimize the use of higher GWP refrigerants. So this is just a kind of a sampling of the refrigerants that are there on the marketplace. I like this slide. It's really neat. Sean, you talked about R454B and R32 a lot this morning. So this slide here, you've got COP performance across the top. So a big number is desirable, and then along the bottom you have GWP. So a smaller number is desirable. Over on the very right-hand side, we've got R744. That's CO2. So the GWP of CO2 is 1. So everything is tied back and compared to CO2. So you think of this chart. Orange is the old legacy refrigerants. Blue I like to call transitional refrigerants, and green is the ultra-low GWP refrigerants. So in terms of low-pressure machines, so that's our centrifugals, and then kind of less than 15 PSI, kind of anybody's centrifugals, not just ours. We've kind of got a solution there. We've got 5114A, which has got decent efficiency, GWP of 1.7. In terms of the medium and high pressure equipment, we've got flames on the low GWP refrigerants. So that's a problem. Sean, you addressed that this morning a bit. In terms of the medium pressure, I see progress with R1234ZEE. That's a relatively low flammable refrigerant. It's quite common in Europe. I think it'll be a matter of time where North America adopts that. We can use that in our screw water-cooled and air-cooled chillers. And then on the high-pressure side, I guess the holy grail would be a low GWP refrigerant that's non-flammable. So industry's got a bit of work, but that we do have some blue refrigerants that are good substitutes for now, and they're less than that 700 GWP cap that you mentioned this morning. And just in terms of refrigerant management, just reducing your fugitive refrigerants, just obviously transition to lower GWP, track and report what you've got, and then obviously maintain the equipment you've got and make sure there's no you minimize the risk of a catastrophic failure. This is a bit of an action plan for refrigerant management. You want to audit the site, keep track of what you've got, identify what you've got, refrigerant charge, look at any service records, come up with an action plan. Action plan would be short-term and long-term. Short-term would be just, complete service, eliminate leaks. Long-term would be an asset plan to replace the equipment. And then you want to make sure that refrigerant that leaves the site is properly destroyed. This is an Excel tool. I guess I'm getting close to time here. So this is an Excel tool. It compares three 6,000-ton plants of three different refrigerants. The bottom line is 514A has a gasoline equivalency of 1,000 gallons of gas or 3,800 liters of gasoline, where 513A, which is, that could be anybody's machine, a legacy refrigerant, is 620,000 gallons of gas, or over 2 million liters of gasoline. So the last thing I want to talk about is renewables. I'll go quick here. Think about renewables. On the left, we've got our energy storage tanks. Middle, we've got wind. But middle, we really have a power purchase agreement, so purchasing from a third power. Typically, that's wind. It could be utility size solar, so 5 megawatt, 10 megawatt solar farm. And then we have generating on site. And 9 times out of 10, generating on site is going to be solar PV. Just some things to think about. You've got the physical aspects. If you're going to do renewable energy on your site, physical aspects, where it's going to go, roof, that kind of thing. Some of the business aspects, enterprise strategy. Are you going to own the asset? Do you want a third party to own it? Is it going to be an energy as a service or power purchase agreement? And then you've got utility costs. So my first solar project was 14 years ago. We received 84 cents per kilowatt hour for a 10 kW microfit system. I think at the time, anything up to 5 megawatts was 42 cents per kilowatt hour. So those days are long gone. I think panels were $6 a watt back then. So fortunately, solar installations have come down in price. But just make sure you understand how you're going to recover dollars. And then the last thing, and this is probably one of the most important things, something I encourage you to do upfront, is identify any capacity constraints. So get with your local distribution company. They should have some vetted process for connecting to their grid, and really open that dialogue up early. So one thing to consider with a solar project is the grid. So we've got 2 provinces here. Well, we've got Nova Scotia on the left, and we've got Newfoundland on the right. So Nova Scotia in 2020, their electrical generation, 73% of that was tied to fossil fuels. On the right, we have Newfoundland, less than 2% fossil fuel. Most of it was hydroelectric. So I guess the silver lining here is if you installed a PV project in Nova Scotia, the GHG reduction would be considerable. You'd really be doing a good thing for the environment. If you installed that same project in Newfoundland, you better have a good financial case, because the GHG impact is going to be almost negligible, almost too hard to even measure. So I guess that's my key message when it comes to renewable energy. There's no one-size-fits-all solution. Each site must be properly assessed, taking into consideration all the unique local conditions. Throughout this presentation, I hope that's come across as a reoccurring message that it's the importance of adopting a holistic systems approach and finding out the most appropriate solution for a specific building. As a leading HVAC manufacturer and solutions provider, we are constantly listening to our customers, and we adapt to their feedback as we strive to make positive change, as we boldly challenge what's possible for a sustainable world. And that,
that is the conclusion of my presentation. Does anyone have any questions? Sean? I hope they're not hardballs around refrigerant.
Well,
I have a refrigerant cheat sheet, so
no, not on refrigerant. I will ask about the ice storage technology. That's been around for quite some time. I'm just curious, it seems like a good idea for load shifting. I'm just wondering, is there obstacles to adopting that I'm not understanding? Why haven't we seen widespread adoption of that technology?
why haven't we seen more uptake?
Yeah.
So number one, you have to have the right rate structure, right? So there needs to be a rate structure where you're incented to shift power after hours. So in Ontario, I talked about global adjustment. If you're a Class A site, above a megawatt for commercial institution, or I think it's 500 kilowatt for industrial, there is that incentive to push kilowatt hours after hours. So we're seeing more interest, more uptake. There's a site in Canada that my team was involved with. I think Ottawa Hydro paid $2,400 per kW for that site to be installed, so that load could be shifted, and that's based on an 8-hour storage. So curtailing 8 hours of chilled water load. So there is interest. Why it's not in every building, I don't know. It is a good technology. If you compare it to batteries, we see a lot of uptake in batteries. Water or ice doesn't burn. There's no connection impact issues. There's no, I talked about connection impact assessment with PV. You have the same issues if you connect battery storage. There's no degradation if you cycle them. You can cycle, freeze the water as many times as you want. It's always going to retain the same thermal properties, where lithium batteries, if you cycle them, they use battery storage for GA curtailment, and they really try to reduce the number of times they use them because it shortens the life of the batteries. So I guess the short answer is, I don't know why the uptake hasn't been greater. I mean, we see a lot of interest, but you think every big building would have ice storage.
Yeah, me neither. The other question I had was around, you showed us a bunch of different technologies. There's a lot of talk around sorbent technologies and reducing the overall ventilation rates. Do you guys have any solutions looking at using sorbent technology in your air handling units to reduce the overall CFM requirements?
So is that absorbent technologies to scrub the air, like using filtration?
Yeah,
specialty
the idea is
filtration
that
to
you
get
have,
by with less.
Right.
Yeah, we do, and I work in healthcare a lot, and unfortunately in healthcare there's prescribed amounts for ventilation. Like it's 6 air changes is patient room, 2 air changes of outside air. So it doesn't matter what technology you use, you're always stuck with those limitations. But yeah, we do have filtration technology. The right applications, you can reduce your outside air requirements, which is, decarb. Let's face it, here in Canada, the grid we have, the climate we have, we're really talking about reducing fuel costs, right? And go back to my statement. You take that energy pie. You've got your skin losses, your roof, your perimeter. Then you've got your ventilation, and then you've got your water heating. That's all it is really in a building like this, right? And if you can cut your ventilation down, you're just going to shrink that overload pie, that overall pie. So it's a good question.
Thank you. Just 2 technologies that I think have good opportunities, and I don't really understand why they're not more adopted.
Well, our uptake. I don't know. There's a couple design engineers in the room. I think the adoption rate takes time, right? It takes time for engineers to get comfortable with stuff and specify, I don't want to blame them, but it's a time issue. Yeah. Any other questions? Oh, there we go. Yeah, I got a booth right over there. There's actually a video going on the ice heat recovery system, ice thermal storage. So it's over there. There's some salespeople over there that would be happy to, talk to you about opportunities.
Do you have to have a lot of space though for the ice back here?
So there, each tank is roughly 8 feet in diameter, 9 feet tall, about, and I'm on the spot here, but in terms of cooling capacity, I think each tank is around 130 ton hours. So, you could do the math quick, and I've got these two big, great, bright spotlights shining on me, so it's hard to do math. But you obviously need space. That building that I talked about and spoke about in Canada, I think they hit 16 tanks. So think about 16 times 64 square feet. That would be about the amount of space required. Those tanks went outside. If we're using them for cooling, for GA busting, they can go outside, they can be buried. I think if you're using them for heating, you'd probably want them inside. I'm not 100% sure about that, but I'm just, if you're going to use them all year round, I think inside is probably better.
Is it pretty cost effective to install them, like build them and install them?
I think in a greenfield application, absolutely. In an existing retrofit, it all depends on the site.
The rate structure too, I guess.
Yeah, you got to have the spot. You got to have you have to have a location. You got to look at the specific requirements. If you're replacing the chillers at the same time and they're at the end of their life, then there's some asset recovery, so to speak. There's some avoided capital costs. So I guess the short answer is it depends.
Yeah, I could see that being one of the big barriers that Sean was asking about, like space is a premium. So if it's a new build and you design it right in from the get-go, sure. But for existing buildings, you often don't have, thousands of square feet of unused space. But
Yeah.
if you can bury it, sure. But then the costs probably skyrocket when you do that. I don't know, but
Yeah, space. Look, obviously you got to have a location for them.
yeah.
Any other questions? All right. I appreciate your engagement, and I thank you for your attention.